Hey, everybody. Welcome. Thanks for taking the time out of your day to come talk to us a little bit about DynamoDB, or hear us talk a little bit about DynamoDB, I guess. My name is Rick Houlihan. I'm a principal technologist for NoSQL at AWS. Many of you may know me. I do a lot of DynamoDB sessions at reInvent and things like that people seem to find popular. I'm going to talk to you today about a tool, generally speaking, modeling practices at a high level, but we're going to talk about a tool that has really evolved from some of the early experiences that my team had trying to help teams model data for NoSQL databases, and this is the NoSQL Workbench for DynamoDB. And so with that, I'd like to go ahead and get started. I'm not seeing the presenter. There we go. It's coming up. With me today is Sean Schreiber. He's one of our senior solutions architects, specialist solution architect, works on DynamoDB team. Go ahead and introduce yourself, Sean.
Hey, my name is Sean Schreiber, Senior DynamoDB Solutions Architect. I have been with Amazon for 7 years, and for the last 4, focusing on Dynamo and living under the shadow of Rick Houlihan. Today, I'm here to help facilitate the discussion. So you guys have questions, drop them into the question bar. Some of us will answer. I'd like to thank our moderators in advance. You'll see their names show up. And the ones that they want me to ask Rick live, I will do that. And with that, I'll pass it back to you, Rick.
All right. Thanks, Sean. All right, guys. So let's get started and kick this off. I'm not going to spend a lot of time in slideware here. We're going to talk about some high-level concepts that are really important when we get into the actual modeling exercise we're going to go through. Sean and I are going to model a real application service for a order processing service, and we're going to talk about how we're going to do that. But I'm going to go through a quick overview just to kind of level set and make sure that for those who are not as familiar with NoSQL as some others, what is DynamoDB? What are the top-level kind of principles that we're going to go through when we start to model data for DynamoDB? What does it mean to take a normalized schema, create a denormalized schema? How do we do that in NoSQL databases? But most of our time is going to be spent today in the introduction to the NoSQL Workbench tool itself, where we're going to kind of build up this application, and you're going to actually see the modeling exercises we go through with teams to kind of define their access patterns, identify their data models, and try to structure things in a way that's the most efficient for them. So with that, let's go on. So as some of us know, and some of us may not know, DynamoDB is a NoSQL database. In NoSQL databases, we have these things called tables or collections, and inside of these collections, we're going to lump a whole bunch of objects, right? Items. Items can have attributes. They can have many different types of attributes, but every item you insert into a NoSQL database has to have this thing called a partition key or a primary key that uniquely identifies the object. All NoSQL databases have this characteristic, and this supports kind of that key value access pattern. Get me the object that has an ID of X, right? A partition key of X. So in DynamoDB, what we can do is we can add a sort key and create a composite primary key, which gives us the ability to kind of create collections of objects that are grouped on into a partition based on the partition key and sorted on the sort key, which gives us the ability to now support one-to-many relationships, complex hierarchies of data, and more sophisticated queries, right? Things like range queries, things between every object in this partition greater than X, less than Y, or between X and Y, things like this. So it gives us kind of the ability to query through a collection of items that are related to each other, actually. And when we do this, the next thing we're going to do is actually start to index these objects on additional dimensions. And when we create these additional indexes, what we're really doing is regrouping these objects. So it's interesting to think, and we'll explain what this really means when we get into translating relational models. But the idea here is that we're creating a collection of objects. We're indexing these objects on arbitrary dimensions that they're define their relationships, and then we're expressing these groupings of objects, or essentially joining these objects on the index, right? So when a lot of people say we can't support joins in NoSQL databases, this is true because we put all the objects in the same database, and everything becomes an index scan, and we'll talk about that kind of what impact that has on the efficiency of the system at scale. But that's really what it comes down to, is what NoSQL databases are all about, is how you can index the objects that are you storing in this repository. And DynamoDB gives us a really nice system to do that with secondary indexes. These allow us to essentially, as I mentioned, regroup the objects on the table on various dimensions. If we might save on our table, we have items that are grouped by customer, for example. In the example we're going to be using, we have customers, and customers make orders, and they make payments, and they have shipments, and all kinds of other things. And we're going to create various partitions that group these objects in ways that are interesting to the application. And some of those groupings will live on the table, and other groupings will live on the indexes, right? And these indexes are going to carry what we call projections, which are the ability to not just store the actual values that we're indexing, but the actual data that's interesting to the application when I go query the index. This makes the system more efficient because when I query the index, I can choose to project, maybe just the keys that I'm indexing. I can support maybe a subset of the applications of the items attributes on the index, or I can project the entire item to the index. And depending on the workflow here, we might project some, none, or all of those attributes, and thereby impact the cost of that index, right? So that's another thing we talk about when we talk about NoSQL data modeling. It's not just the structure of the data, but it's the efficiency of the access pattern, right? Do we have a write-heavy workload, or do we have a read-heavy workload? Maybe an expensive read is actually okay if it's an infrequent read, right? Maybe if I have a high-velocity write pattern, maybe having an index to be able to find very quickly an exception item would be great, but I'm going to be hitting that index a lot, and it might be better for me to just scan the table and find the exception items intermittently if it's an infrequent pattern. Anyways. We can talk about that when we get into the data modeling constructs and why do we make choices. Why do we create indexes versus table scanning and things like that. But generally speaking, it's about modeling the data. And as many of you know, when I talk about data modeling, what we're really talking about is relational data. There is no such thing as a non-relational database, I like to say, because there's no such thing as non-relational data. And really what we're dealing with is denormalized databases versus a normalized data store, which is what they traditionally call the relational database. But just because I'm changing the data model doesn't mean that this relationships between the data structures just magically goes away, right? We're just going to maintain these things in different ways. And it doesn't matter what type of application you're building, we're going to create data structures that are linked together via pointers, so to speak, and indexed on secondary indexes and grouped together to express these relationships, right? So what happened? Hang on one second. You have a question?
So
Sean?
we've gotten some kind of feedbacks. One person said they really love DynamoDB, so they're happy to be here. So I thought that was kind of funny. And then another comment was about my microphone being a little bit too loud, so I turned it down a bit. So hopefully we're sounding pretty good to you guys. Do keep those questions coming. Any questions you guys have ever wanted to ask Rick, let me know and I can field them.
Yeah. We'll try and get as many as we can in. We do have some pretty thick content. So save the questions if you can until we get into the actual Workbench tool, because that's when I think people are going to be interested in what we're doing there. As we model the data, again, some of you may have seen this already. We're talking about taking these relational structures. This is a simplified product catalog. We have a one-to-many relationships between products, or one-to-one between products and books, products, albums, and products and videos, one-to-many between albums and tracks, and a many-to-many between videos and actors. And we would have a whole bunch of different queries we would write to be able to extract different products and different types of products and create a complete product list. In a NoSQL database, we'll do this a little differently, right? We'll create some hierarchy of data inside of a blob, in this case, maybe a document structure. And that's one way we could structure this data, but it might not be the best way. And what we're going to actually express today when we start to go through the modeling is really this concept of partition overloading, where we're going to be taking all of these rows, so to speak, and we're going to create individual items that live inside of these partitions, right? So in this example, we have a customer. A customer makes orders. Orders have items. We have some date-ranged collection of orders and order items inside of this customer's partition. And we could have some queries that would extract this data in various ways. But the idea, again, is we're going to create partitions on our table partitions on the indexes. Inside of these partitions, we're going to have sorted elements, and we're going to query against these sort keys with specific range conditions or equality conditions and extended filter conditions to get the objects back out that we're interested in, similar to how we try to carve through these relational structures with our ad hoc queries, right? And the reason that we don't necessarily want to use those ad hoc queries is because they're more or less they're more expensive, right? And so let's take a look at what that actually looks like when we get into expressing SQL statements and running this actual workload. And at small scale, this isn't terribly expensive, but at large scale, it gets very expensive. And this is part of the exercise we ran through at Amazon when we started to look at migrating our relational workloads, which were breaking even the largest of large Oracle rack deployments. And it was amazing what the CDO teams were pushing through these systems, and we were breaking every relational database at scale. So we kind of had to figure out how to do things more efficiently in order to scale. And this is really, it demonstrates the problem we ran into. So if you look at these simple joins, just a one-to-one join between two tables or one-to-many join, we have a time complexity that comes down to basically log n plus n log m. And that's just one join, one table. As you start to go through these tables and select on different, more complex structures, the time complexity just increases. And this assumes that these tables are properly indexed on all the right join dimensions, and we're doing nested loop joins. We're not doing hash joins, which get terribly complex. But when you start to look at how the relational database breaks things down, the complexity, the time complexity just magnifies. The more tables we join into the system, the more, the higher the time complexity of those queries. And again, at small scale, no big deal. These individual queries are not all that, expensive. Maybe if you're running at high velocity, you might run into these problems. But at large scale, these things break your systems. And that's what started happening to us. So when you started to move to NoSQL, again, what we're doing is taking that exact same data model. I'm taking all the rows from the relational data tables that we have here, and I'm collapsing those rows into a collection of objects on the same table. Now what you can see is it's kind of interesting, right? Those product groupings are kind of created on the table for me. I have, if I want to go and select out of the book partition for a given book, for example, in an optimized NoSQL implementation, you're looking at a time complexity. It's a distributed hash table, right, which is theoretically constant, time constant. Now, realities of implementations aside, that's probably an O log n because we're scanning an index at some point. But the point here is it never gets worse, right? So as we start to join more complex data structures, and essentially these rows are pre-grouped into these partitions, so the time complexity never increases. And that's one of the best, that's the magic of a NoSQL database, right? We kind of pre-join the data by creating partitions, loading these overloaded object types, multiple types of objects into these partitions, and then using simple queries to pull back these related items. And this is an interesting data structure here. It kind of demonstrates the relationship between an actor and a movie, right? In this case, we have the movie Big, where it was directed by Penny Marshall. We had multiple actors. They had multiple rows, and actors themselves have partitions on the table. So this is what I would call a directed graph structure, right? More or less. We have the movie, which is aware of the nodes that he's connected to, the actor nodes, what roles those actors had. There's some properties that are specific to the movie. We've got some immutable data that we projected onto these edges so that when I get the movie summary, I can get a full view of what I need. If somebody comes into the internet, oh, Tom Hanks, let me see what other movies he's in, right? He can go click on Tom Hanks. Well, Tom Hanks actually knows nothing about what movies he's in according to this data structure, right? So how do we rectify that? And the way to rectify that is to take that partition key and the sort key and flip them around, right? So now, and what we're going to do is we're going to create a GSI, a global secondary index, and we're going to take the sort key of the table and we're going to make that the partition key of the GSI. We'll take the partition key of the table and make that the sort key. And what becomes interesting now is we kind of completed the other half of the graph we talked about, but we've enabled a whole new set of access patterns, right? I can go get all the books for a given author. I can go get all the albums that the song's been on. I can go get, all the movies that an actor's been in. So there's the other half of that. Now we have an undirected graph. And the best part about using DynamoDB for this is that I don't have to maintain this relationship. All I have to do is enable the GSI, right? And now all of a sudden I have this self-maintained, essentially graph structure, right? So it's a single level graph. Again, we go through other access patterns here. We've got what movies a director directed. We've got what albums a musician produced. Again, so wide variety of access patterns just from flipping those two keys around. And in this case that we wanted to do that, in some cases we might not, right? If I don't want all the items in the table to project to the index, and there could be valid reasons for that, we might talk about that when we get into the modeling discussion. But in this case, we wanted all the items on the index, so flipping those keys around just completed the other side of some relationship that was interesting to us. And that's really what we're doing, again, when we model data for NoSQL databases. It's about creating partitions on the table, partitions on the index that are meaningful groupings of items that your application needs to process the workload you're asking it to process, right? And again, understand that when we design these data structures, they're finely tuned to the access patterns, but generally speaking, that's actually a good thing because the access patterns are consistent over time. They don't change, right? With an OLTP application, it does the same thing a million times a day. It doesn't do a million different things one time a day, right? So that's where NoSQL starts to work at scale. All right. So let's talk about the application that we're actually going to model that Sean and I are going to work with here. This is it's basically a simple customer order processing workflow. Customers make orders. There's a one-to-many relationship between customers and orders. And typically the process I go through with the team is exactly this. We'll sit down and we'll talk about, okay, what are the entities of your application? What types of data are we trying to manage? And how is this data related? Because once we understand how it's related, then we can start to define how you're actually accessing it. And so this is the idea. It's a pretty common process you go through with just about any application, or you should be going through, and it's quite a misconception that NoSQL databases don't require any data modeling, because they absolutely do. I mean, there is a good use case for a blob, key value blob store, but this is not that, right? I mean, most applications are not very simple key value patterns.
So when you say, orders like this, I'm thinking something like an Amazon.com. Is that what you have in mind when you think of this system?
Yeah, you could think of it this way. This is what, I mean, I guess the invoicing and payment workflow that we're talking about here would be more of a vendor relationship that you would expect, right? Where I have a manufacturer and I have multiple customers that I'm shipping product to, and then I would submit invoices and receive payments. And this is not necessarily an Amazon type.
More on the procurement side.
This is more of a
I need to acquire the parts, all the assemblies for my product.
Sure.
Okay.
Sure, it could be a manufacturer, could be a retail distributor, but somebody who has commercial accounts or something like that, right? Anybody. It's a pretty common idea of a workflow. Again, so customers make orders. Over time, orders have line items and they have shipments associated to those line items. So there's kind of a many-to-many relationship to the orders and shipments between, and kind of related through the line items. Orders generate invoices. Invoices are also associated shipments. So again, we have this kind of multiple many-to-many relationships that we're trying to map and model here. An invoice can have one or more payments depending on the customer and the terms you have with the customer. It might have credit associated to that. So a relatively complex data model, even though not a lot of entities here. And for this particular application, what we kind of came up with was these 14 different access patterns. And I'm not going to go through every one right now because we're going to address these when we actually go into the NoSQL Workbench and start modeling the tool. And just give me a second here because I have to log into my other system where I have the completed model set up so I can compare what I'm doing to what what it's supposed to look like, which is obviously what we're doing here. And we're going to go into the NoSQL Workbench for DynamoDB. So this is a really good tool. It was designed by and for the AWS Specialist SA team as we work with our customers and the engagements that we go through constantly, which is this design process of identifying the patterns and identifying the model. And it allows you to model data, visualize your designs in a way that we feel is very unique and very relevant to almost all NoSQL databases. You can download it. Here's the URL. And the charts will be available after this, so you'll have access. And you could just Google the search term, and you'd find it up there fast enough. Okay, so what we're going to do right now is I'm going to exit off of this presentation, and we're going to go to my screen. All right, and so here's our NoSQL Workbench for DynamoDB. And this is what you're going to see when you open the tool up for the first time. We have a couple sections on the tool. The first one's going to be here's your recent data models and what have you done with this tool, which at first you're going to have nothing that you've worked with. There's some sample data models in the tool, I'm not a big fan of these models. I think that they're obviously most of these are flawed, but they do demonstrate, some of the characteristics of DynamoDB. So I would definitely look through them and understand things like projections, things like some of the hierarchies that are built mostly in the advanced models. They're definitely worth looking at. But for our exercise today, what we're going to do is create a new data model. And this data model is going to be, again, that order processing workflow. And we're going to look at what happens when we go through the process of building this model. I'm not going to worry about description. And so when you go into the create, the first thing it comes up, it says define some schema. So again, just because it's NoSQL doesn't mean we don't need schema. We need at least a partition key, maybe a sort key for the table, but we're also going to put some other things on these items because, like I said, the key thing here is we want to index and group these items in a meaningful way. So the first thing we're going to do is add a table. That table is going to be our order processing table. And it's going to have a partition key. I like to use generic key names because, again, if you think about it, I'm sticking all kinds of different types of items in here. So if I have a strongly typed name for a partition key like customer ID, then everything I stick on the table must have a customer ID. And I don't know if necessarily that's going to be the case. As a matter of fact, I'm kind of sure it won't be. So what we're going to do is define our first key for the table, which is going to be a partition key and a sort key. And the first access patterns that we had were pretty straightforward. They said, hey, I need to get a customer by ID. I need to get an order by ID. I need to get shipment by ID. I need to get invoice by ID. Okay, so that kind of tells me right there I've got at least four different types of partitions that I'm going to put on this table because each one of those items needs to be selected individually by its ID. Okay, so let's go ahead and add another attribute, which is going to be the type. And that's also going to be a string. And so right now, if I wanted to, and I actually think this is probably a good place to start, let's go ahead and commit this definition to the table, and we're going to go ahead and visualize the data model. It's pretty straightforward. It's pretty simple. We're going to add some items to this table that are going to be exactly what I said, those particular types. So in this case, we're going to add a row. It'll be the customer ID. It's going to have the sort key we want to put on here would also be the customer ID. And this is because, I need some sort of sort key on every item because I defined the table with the partition key and a sort key. So every item needs that. It might not necessarily have more than one item in the partition. It may or may not, depending on the model we're building. But for this particular example where I'm just saying I want to select these four types of items by ID, it won't, but we'll eventually get more complex. So it's a type customer. We're going to create another item called an order ID. It's partitioned on order ID. It's also sorted on order ID, and it is type order. Now, orders have items, right? So let's go ahead and add those items. We don't have a workflow that says select by item ID, but we know orders do have items. So let's add a couple items to that order. And that is an item. And then we're going to go ahead and add another item. And this will be item ID 1. That is also an item. And now the reason I add type to my objects is because I always like to be able to do some sort of validation of the object structure. This is pretty common when I work with enterprise customers, when I work with larger customers. Not so common when I work with smaller customers because a lot of times small teams don't think about stuff like this, but I do recommend you do think about this kind of stuff because when you start putting things in the database, you kind of want to know what you're putting in there. So having a type designation on the item is a pretty good idea at any given time. Wherever you want to stick that could be inside of a data blob or whatever on the item, but for this particular example, we're just going to declare a top-level item on type. What was our other access pattern? So we had get customer, get order, get shipment, right? So let's go ahead and create, I believe we want some shipment items. Let's go ahead and look at my sample table here and make sure I'm not making a mistake. Yes, we want shipment and invoice items. So all right, so the shipment items will actually be sorted on the order ID. and we'll get into why that is later. But bottom line is I need to know what order the shipment is for. And so this is a shipment. And we're going to have another shipment that's going to be shipment ID 1. So this will be another shipment associated with that order. Because remember, we had a one-to-many relationship, a many relationship between orders and shipments, right? So we can have many shipments for orders. So let's go ahead and model that. So that will also be for our order ID. That is also a shipment. Okay, so let's save this real quick and take a look at what our table looks like. So right now what we've got is we've got a table that says I could select an object by customer ID, I could select an object by order ID. I made a mistake. Let's go ahead and update our data. Stop that. Data. One of those isn't right. All right, so I've got an order. It's got 2 items, and it has the order object. Now, when I model data, I don't really do a lot with projecting all the extended attributes because what I'm really interested in is finding objects. The way you find objects is by looking at keys. So what I'm really doing is structuring the keys. I'm not terribly worried about having, the 100 extra attributes that define an order or whatever, right? I just need to know, okay, here's the keys for the order object. When I go into production or when I go into actually put real data on a table, there may be a whole bunch of extra, attributes, and I'll usually store those in a map that I'm going to call data. So every object here on the table will have a data map, and that'll just be all the unindexed attributes, the things that make up the object, right? If I have projections that need to be made, I'll create a data object, I'll create a p data object, and in the data object I'll have the unprojected data, so that when I define a GSI, I can say, here, key on this and project p data. That allows me to be very flexible with my GSI definitions. I don't have to worry about specific attributes that need to be projected. So remember that when you're modeling your data, if it's not an indexed attribute, it does not need to live at the top level of the object. And therefore, I don't really need to see it in the workbench unless there's a specific reason that you're doing that. Because all those extended attributes, for me, tend to kind of make the screen messy. I prefer to have more real estate to work with. Right now, this is a simple model, so plenty of real estate. But when you get into complex keys, lots of GSIs, and you start losing real estate pretty quick. So only view what you need to view is kind of my approach here. So at this particular point, I can select by customer ID, I can select by order ID, select by shipment ID, and I had the other access pattern, which was to select invoices. So we haven't created any invoice partitions yet, so let's go ahead and do that. Create those partitions real quick. And invoices are sorted on order ID, and that is an invoice. Now, the other thing that invoices have is invoices have payments. So we're going to go ahead and add payments to our invoice. And that is a payment. We can save that. We can take a look at our model again. Now we have an invoice. Invoice partitions have order ID objects. They have payment ID objects. So if we want, at this point, we can go ahead and commit this data to DynamoDB. We're not necessarily going to do that yet because we have some additional access patterns that we want to actually demonstrate here. So we're going to go back to our designer and say, okay, what other groupings do I have to support? I have my top-level access patterns, select by customer ID, order ID, select by shipment ID, select by invoice ID. But now I have additional access patterns that we want to support. So what were those? Those were get order history, right? Get customer history by date range, get shipments by order ID, a variety of other access patterns. So let's talk about get order history, right? How are we going to go get order history here? We're going to go back and create an index. So the first thing we're going to do is we're going to add a new sort key, a new partition key for our index, and edit that table definition, add a global secondary index. And for this, we're going to have to add some new attributes, right? So a new attribute type is going to be PK1, and we're going to have another attribute type. It's called SK1, and these are going to be for our GSI, which is going to be called, hey, creatively GSI1. Why do I call GSIs by these types of generic names? Because not always do these GSIs support only one type of access pattern. If I name the GSI by access pattern, then I'm kind of, maybe stuck with that. I'd rather use a generic name and know what access patterns this GSI supports. Now I can go. Oh, go ahead, Sean.
In this pattern, it's GSI index overloading. I always wondered what happened to the GSI1 underscore PK, and that is answered. I actually think it's a little bit better to come in with a shorter attribute name for your GSI.
Go ahead.
And I have a question about the NoSQL Workbench from Bronislav. He asked about the connection between the NoSQL Workbench and a relational database. Earlier versions of NoSQL Workbench allowed you to create queries against I think it was a MySQL database. So do you think that'll come back in the future?
That's probably something that will return. The first implementation, I think, was a little rough. People are having trouble with it, but it's something that's still on the plate. I believe I wouldn't necessarily write it off. The tool is built to connect to multiple data sources to try and push data into DynamoDB, and what you will be able to see over the next coming months, years, and future of this tool is more expanded connectivity, I'm sure.
Awesome. And I have one more question, just a clarification about the model. Could you explain again why the duplicate partition and sort keys, for example, shipment ID 1 and shipment ID? So why is that attribute in there twice? The reason I'm doing this is because I'm trying to demonstrate that there's multiple shipments for this order, right? So that's why there's actually two shipments. They're both shipment IDs, but one is shipment ID and the other is shipment ID 1. And the reason why would be, again, to demonstrate that one-to-many relationship between, the orders and the shipments, right? That makes sense.
Okay, so let's go back to our data now. We can start to edit the data and, visualize data model, update and edit the data. And we can start to add our new partition keys in here. So what we really want to do now is identify all the things that are associated with order, we want order history, right? Was that our next one? Is that get order history? So what happened to this order over time? What was the sequence of events that happened within this order? And, what are all the objects that are associated with this order? So on when did payments happen? So everything that's associated with a particular order is going to go ahead and get its order ID as PK1. So again, we're going to duplicate that key multiple times across the object, and it's the same as if I was joining on multiple dimensions in a relational data structure, right? I need to be able to index these attributes in order to be able to group objects on those attributes. So the items that are on the order would also have the order ID tagged on that particular key. We would tag. Stop that. Oh, I hit the caps lock. Shipments are also on this order ID. What happened here? Let me just go ahead and paste. Paste is a better thing to do. Shipment 1 was associated with order ID, with the invoice that was associated, the payment that was associated. And then what I'm going to do is I'm going to put a date string of these particular elements. I'm just going to use today's date, which is 2020. What is the date today? 6/10? Yes. 06.
Yep.
-10, and we can just say this all happened at midnight or at noon, right? And so what we're going to do is just put some placeholder dates in all these things. And so what we're really doing is getting a date range list of items and invoices and payments and everything that happened to this order, right? What I've done is I've now created, there's a single partition on this GSI because the objects I've entered in here are all related to order ID 1, and they all theoretically happen on the same time. And what we would end up doing then is seeing that when we go to our aggregate view, I can see here's my table partitions, but I have this new tab here. It's the GSI. But there's a mistake I made again in my data. Let's go ahead and find that. Edit data. There it is. Copy paste. As you can tell, my typing skills are not as good as my data modeling skills. That's okay. I don't have to type much. When we go into GSI now, we can see this order partition. I would have a date range list of items that were associated to that order, all the order itself, the items on the order. I would have the shipments that were made, when they were made. I would have the invoices that were sent, when they were sent. I would have the invoice and the payments that were made. So I've satisfied that access pattern by creating that nice little GSI. Right, so this is what we can start to do with our data to manipulate things and make things, regroup to the various dimensions that we're querying on. Our first 4 access patterns on this, our 5th pattern on the GSI. All right, so let's go back to the data. Let's take a look at what else we need to do. I now have to get customer history by date range. Okay, so that's since most of the objects that I have on the table are already appearing on GSI1, I really don't have much of a choice here but to create another index. Because I'm kind of indexing all dimensions, all items on the table by order to get the time history of items by order, and I need to extend all those items or I need to group those items in different dimension, which is customer by date range. So let's go back to our order processing table in our designer. We're going to add some new attributes to our table, and these are going to be PK2. And do I really need another do I need another sort key? Probably not, because I already have a date in sort key 1. So I only need another PK. So I'm going to go PK2, and I'm going to create another secondary index that's going to be GSI2, and GSI2 is going to have a partition key of PK2, which is going to end up being the customer ID, and it's going to have a sort key, which is an SK1, because SK1 is the date, and that's what I want. I want order history and I want customer history, right? Both by kind of date range is really what we're looking at. The order history is just a complete list, but in this particular access pattern that we're trying to get, orders only, you want the summary list, but customers, maybe I only want customers order history for the last 30 days or activity for the last 30 days or something like that, right? So, and again, we're assuming that customers in this case are not these massively monstrous conglomerates of corporations that can order tremendous amounts of volume. Most of these items we're creating on these table are relatively small, and it's actually, with 1,000 writes per second, you can do a lot of ordering and a lot of grouping of items onto the table by customer. So that's another thing to consider. We're not going to talk about today, but if you need to scale NoSQL databases, obviously you need to go horizontal. A lot of the patterns we're talking about today are kind of grouping everything into one partition. If you need to get things spread out at high scale and high volume for some of your workloads, then we want to talk about write sharding. That's probably out of the scope of today's discussion. But suffice to say, most of the aggregations that we're building today support that kind of 1,000 WCU idea for these aggregations. So let's go ahead and commit this to the schema. So now you can see we have 2 GSIs. We have our one table. GSI1 is on PK1, SK1. GSI2 is on PK2, SK1. And we're going to go ahead and update our data to be able to reflect this new dimension. And so in this case, all of these objects are grouped on, hey, guess what, customer ID. And so we can go ahead and tag customer ID into PK2 for all items. So it's kind of interesting what you can see what's happening here now. These items are getting grouped on multiple dimensions. Oops. And we can go ahead and see that some items are not all on all indexes, right? So its customer ID has no logical grouping by order ID. It's just being dropped off. So none of those customer items are actually going to project to GSI1. Only the order objects and the objects related to the order are going to project to GSI1. However, all of the objects will project to GSI2 because that's an aggregation by customer. So let's take a look at what GSI2 looks like. And we can see we have our customer partition, and we have our date range list of items associated with the customer, what orders he made, what items he ordered, what shipments were shipped, when they were shipped, invoices, the whole 9 yards. And so this is a really good example of how you can add additional, support additional access patterns by creating, additional indexes. The next access pattern, the next index we'll create is actually going to be what I like to call overloaded, because it's going to support multiple patterns. These 2 indexes could be named, right, strongly typed. This could be order history. This could be customer history. And the reason why is because, all these objects from the table are actually projected to both those indexes for the most part. And so the way that you're going to actually query objects across multiple dimensions is to do, add these objects to multiple indexes, right? That's what you're kind of seeing here. As we build the model, we're extending the keys and the collections of keys across the items to be able to create these more complex or support additional access patterns, not necessarily more complex, right? Anyway, so let's get into the next set of access patterns, which would be select shipments by order ID.
And if you would like to see those access patterns, I took the opportunity to grab that image from the slide with just the listed access patterns, and it's in the Q&A. So check out the Q&A. There's an Amazon short link. It'll take you to the list of queries, the access patterns that we're working on right now.
So the next access pattern on the list that we're trying to support was get shipments by order ID. To get the shipments by order ID, we actually already have it, right? I mean, I can select all the items by order ID. So what can I do? I can select the objects off this table by order ID and filter on the PK equals shipment or starts with S, right? Because we know that all shipments are going to have a type indicator on their partition key. That's typically what I like to do when I create objects. Is one way to designate type is obviously have a type attribute. And I also like to put some sort of a leading indicator when I need to do these filter conditions. Or heck, I can filter on the type, right? I can say, select from, all from GSI1 where the order ID equals X, filter on type equals shipment, right? And that's actually the query I would execute, because what I'm doing is knocking out everything that's not a shipment. And the reality is an order is not going to have, 1,000 items. And if I add up all the RCU of all these items, it's probably likely to be 1, 2, 3 RCUs maybe. It's actually just fine every now and then when I need to run this access pattern to burn a couple RCUs to avoid having to create another index, right? If I create the index, then I'm going to have to maintain storage. I'm going to have to maintain capacity. I'm going to have to pay money for those writes. Every single time a shipment is written, it's going to get written to this index and every other one that I'm going to define for it. So let's make sure that I'm reusing the index as much as possible when it's relatively efficient. So if the read pattern is, say, get me all the shipments for the order ID is infrequent, which in this case it probably would be, because we're saying this might be a customer support workflow, that's probably going to be infrequently read, then maybe I don't want to optimize for that read. I'd rather say let's have a fat read and optimize for the write. So you get into these discussions a lot when you're talking about how to create your data model. Do developers constantly make a mistake, erring towards optimizing the reads? It's something. It's like in our nature. We love things that look pretty, but sometimes that table scan is just fine. So in this case, we're scanning the whole partition and kicking out the items that aren't shipments, but that's 5 or 6 items for most orders. So let's not worry too much about that. Next access pattern is get payments by invoice ID. So this is going to be a table access pattern. We've already got it, right? I can select by invoice ID, and I can say where the type equals payment, right? So that brings back, heck, I could might as well bring the whole invoice back to the app. It's a very small amount of data, but who knows? Maybe the top level invoice item has 100 extra attributes. I don't necessarily want to read all that or transport it to the client when all they really want is the payments for the invoice. So you can select by invoice ID, where type equals payment is a filter condition. Again, knock out the order ID. Let's go to next access pattern would be get invoices by order ID. So what do we have here? We have, again, an access pattern that says PK1. This is GSI1 read. There we go. Get the invoices, so we can select from GSI1. Again, we've already built the data structure. We've got the order history, so I can select from here and where the type equals order, right? There should be something in here where type. Yep, there we go. So we can go get the or invoice. I'm sorry, type equals invoice. So I can select from the order history GSI on GSI1 where the type equals invoice as a filter condition. And for the same reason, I wouldn't create another GSI to support that specific pattern to return only one item. It is because it would be an infrequent read, right? If it's not necessarily a frequent read, then again, optimize for the write. Don't pay the extra cost for storage. Don't get the extra index. If we want to get payments by order ID, we do the same. If we want to get we already did that one. If we want to get the orders by item ID by date range, Okay, so in this case, what we're doing is going to create, well, now we have to create a new index, right? I actually have to create an index on the item ID. What I'm really looking for is who all ordered what, when, right? This is a pretty common access pattern. We have it in Amazon Retail, and so this is not going to be supported by the two data structures, there's two secondary indexes we have defined. So now we need to go create a new secondary index. This is going to be back to our designer. And we're going to add a new partition key. And again, this is a date ranged collection of items, so we can reuse our sort key that we already have defined. So let's go ahead and do that. We're going to create another attribute. This is going to be PK3. And we're going to create a new GSI, which is going to be GSI3. It's going to be partitioned on PK3. Going to add a sort key, which again will be the date range key from our GSI1, and we're going to go ahead and save that. Now we can go back to visualize our model, and we can edit our data to add the new partition key aggregation. All right, so we want items by date range. So in this particular case, we have our items. These are our items, and these are going to be partitioned on item ID. So this is item ID, item ID1. Right? And I think that's all I want on there. We want orders by item ID by date range. Yes. This is going to say, if we save this data, and we go look at our aggregate view, now we have GSI3. You can see the date range list of orders by item ID, right? So now if I need to, what I can do is in the extended data of these items, maybe I can project some top-level metadata from the order. Let's say so I don't have to go back to the order object and find it. When I create the order, there's going to be a set of immutable data that's going to be created, right? Like customer PO number, freight type, all these types of things that are selected that become immutable. Then I might say, well, when I make this workflow call down to say what orders were, what items were ordered, what I'm really looking for is, what's the most common shipping method for this item when people order it over the last 12 months. So maybe I'll project that data into the item when I create it and add it to the order because it's immutable. It exists at the top level order, and I don't want to have to go back to the database to go get that. I can just tag it in here as an extended attribute in the data blob of every item, for example. So that'd be a good use case for denormalization, right? But what I'm really looking for here, again, date range list of order IDs by item ID, and that's what GSI3 is giving us right now. And so what we're going to do is with GSI3, since we look at the table and I look at the data that's on the table, only two of the items on the table are actually defined for GSI3, right? So GSI1 gives me everything but customer objects. GSI2 gives me everything. So GSI2 is pretty much everything that's hitting the table right now shows up here. So GSI2 is a single purpose GSI. GSI3 is only indexing, a subset of the items on the table, right? The actual order items are showing up there. So we can reuse GSI3 if we have other access patterns for the other objects that we're putting on the table. All right, so let's take a look at the next access pattern. We want to get items ordered by date range by customer. Okay, so in this particular case, we're going to actually look at, this is an access pattern we can support on GSI2, right? We have customer ID. I can select where customer ID equals X. I can select between date 1 and date 2. That's our sort key. And then I can filter on type equals item. Right, so I can say, okay, great, I don't care about the entire customer history. I just care about this chunk of history between date 1 and date 2, and I really only want to see the items that are actually ordered. I don't care about payments and invoices, shipments, and all that stuff, so I'll just add the filter condition and bring that back. Again, I'm assuming that this is this could be a regular read, but it's relatively infrequent. If I look at our retail systems, we do scans like this through the table spaces, looking at different things like this across customer spaces, once, twice a day sometimes, or weekly. I wouldn't expect that this would be an access pattern that runs at high frequency. And then we would say, okay, get the invoices for a given shipment. Okay, so now what I can do is I can take the items that are actually shipments from the Yeah, so we're going to go ahead and index these. Let's see. Let's go back to our data, and I'm going to take shipments, and I'm going to invoice these guys by what was it we wanted to do? What was our dimension here? Get invoices for a given shipment. So now invoices have a shipment ID. That's all I really need to do, and then I can index that. That's how I'll tie these to these items together, right? Invoices have a single shipment. They're tied to an individual shipment, and so actually I would need to add a new invoice to the table. Let's go ahead and do that real quick. And we're going to go ahead and have a couple of payments. And this guy's going to have And so what I'm doing now is I'm modeling some of the one-to-manys that cascade through that entity relationship diagram. Since, orders could have many invoices, I'm not modeling many payments for an invoice. Each one of these invoices has a single payment in this particular model. And this is going to be an invoice. And what I could do is I could just make this, here, we'll model the one-to-many right here. Now invoice 1 has no payments, but the initial invoice has 2. This would be a payment. These would all be related to the same order. Oops. And so this is an exercise I end up going through with teams. It doesn't, as you can see, we haven't really even been at this too long. We're starting to develop a pretty complex model. Again, these are all related to one customer. And that's really what this schema is intended to do. It's intended to model what the table looks like. What are your partitions? When I have an order partition on the table, what's in that partition? There's items that are associated with the order, and there's an order object, so on and so forth. When I create the partitions on the GSIs, what kind of partition is it, and what's in it? So now if we look at the individual on GSI3, I can query GSI3 by shipment ID, and I can actually go get the invoice ID that belongs to that shipment. Again, I can choose what to denormalize into that item on the shipment. When I make the shipment, is there any top-level metadata from the invoice that I want to denormalize, so that when I make the call down to the GSI to pull up the shipment by ID, I already have the data from the invoice that I need for that workflow, right? This is the kind of stuff we're going to make a decision. Do I really just need to identify the invoices? Do I need to have some of the data that lives in that invoice? What is it that I want to actually project down there? When I'm doing this kind of denormalization, I really try to use immutable data, right? Stuff that doesn't change very frequently, because I don't like having to go back and clean up breadcrumbs, right? This is something people always complain about. If I have highly mutable data, then what I'm going to try and do is create these indexed partitions that group that data in such a way that, when I query the customer partition, for example, if I want to get everything in the last 30 days, why am I not seeing the customer object here? Oh, because I didn't have a sort key 1 string here. So in the customers, this is here. Let's put an example here. If I have a customer's sort key, which is, let's just say this guy has a record which might be an alphanumeric. So it's a record, for example. Now, if I save this data and I go back to the aggregate view and I look at the customers by data, the last item here is the A record. If I say greater than 30 days ago, give me all the customer's activity for the last 30 days. Well, I get everything that the customer did in the last 30 days, plus I get the customer's metadata, right? So you can start to, use these very interesting use cases where I can make one call to the database and populate a dashboard, for example, with everything I need. I don't have to make multiple requests for all the different types of objects. I don't have to go get a select, individual metadata for the customer on a single request. It's a much more efficient way to model the data. Right, so these are kinds of things that you're going to want to do when you start to actually look at the data. How can I group data effectively for the application to minimize the number of round trips that I'm taking and to maximize efficiency? Everything you do when you model your data for NoSQL is going to be geared towards, what is the frequency of the access pattern that I'm trying to support? what is the nature of the optimization that I'm trying to make in the model? Am I optimizing for the read? Am I optimizing for the write? These are all considerations we want to make, because it might be a wildly different query that we'll design and data model that we'll design for a very infrequent access pattern that we versus one that happens a million times an hour or something like that, right? So these are the things that we're going to want to start to think about. So the last thing that we're going to want to do is we're going to want to get shipments by carrier type and date range. So in this particular case now, let's see. We're going to tag our shipments objects here to get this last use case identified. Let's go ahead and take this. So see, now shipments don't yet exist on PK3, so how are we going to tag these shipments? Well, let's say, hey, this is a USPS standard mail. Right, and so this one was, USPS, we'll call it standard mail too. We don't need to have multiple, partitions, but you can see, I can basically, what I'm doing is I'm taking my shipments and I'm spreading them across, carriers and types of, methods that they're being shipped. And when you look at our overloaded GSI3 now, we have a partition for each carrier and type of shipment, and we're able to, process up to 1,000 items a second into those partitions. And I can say, give me all the USPS standard shipments for the last 30 days and paginate through that result set if I need to. So you can use the partition key to kind of essentially spread the workload out. We talked a little bit about right sharding. This is kind of right sharding. Let's say my organization, each individual carrier and method of transport didn't exceed 1,000, but the aggregate of all carriers and all methods of transport did. Well, I can use the partition key here and shard it on type and carrier to be able to spread the workload out, so to speak. So I can query individually by type using a date range to get that list of shipments, right? So that's the final way that we would overload that index, I believe. And in the end, what we have is a pretty nicely rounded out model here, right? We've got, and this is one of the reasons I really like this aggregate view, because it gives you a really good idea of what things are going to look like on your table in production, right? And so I'll typically build these types of models, and I'm using really generic names and things like that. And like I said, I'm not too worried about the extended attributes and the extended metadata, because it's not really involved in the query path, right? And the query path is about keys. Sometimes those filter conditions, you're going to want to filter on the objects that are on the attributes that are down inside those blobs. As a matter of fact, I would say, this type attribute that we have here, this could live inside of your data blob. It doesn't have to be a first level attribute. We're not really indexing on type. You could theoretically say, hey, get me all shipments. I could create another index, and instead of calling this type, I'd call it PK4 and create a PK4 on type, and be able to query across all types of objects and all the types that were created in a given date range. And that's kind of gives you the idea of how flexible things really are here. I don't necessarily have to tie myself. And this is something that actually, my opinion of this has evolved over time as I've started to actually have to address, complex applications and not just, roll these things out to production, but have to maintain them. I've now had to work with the teams that have built the models that we first advised, years ago, and are coming back and saying, now we need X, Y, and Z. And I'm really starting to find out that other than, having to do some sort of table scan and write back operations potentially, most of the time what we do is kind of a lazy, transformation of the data on the table. As data is read, it's written back in the new form. And what we're really doing is extending the model, right? We're adding new dimensions of aggregations, new indexes, overloading existing indexes with items that previously didn't exist on them, and basically creating, new access patterns for existing data on the table. It's not so painful as you might think. Even doing it at scale, it's not terrible. So the other thing we want to start showing, so the model's fairly complete here. We've addressed all 14 of our access patterns. Primary access patterns on the table, pretty straightforward. Those 4. We have the one access pattern on the order GSI. Again, why? Because, well, most of the items were already appearing on the index. The only ones that didn't were the customer items. every item appears on the GSI2. So these are relatively special purpose GSIs, but GSI3 is kind of our Swiss Army knife, right? We're just saying, okay, I can index items this way, I'm going to index shipments that way, I'm going to index, invoices in another way, and we can get a much better multiple use cases supported by GSI3. And that's typically what you'll end up seeing, is that as you extend out to your GSIs, fewer and fewer items will project. I mean, I don't necessarily need to index every item on the table 3 ways. I don't need to index every item on the table more than 1 or 2 for most typical applications. So, but some items, I need to index 4 or 5 times. DynamoDB supports up to 25 GSI, so believe me, you'll never run out, especially when you can overload things like this. I never typically go beyond maybe 4 or 5 GSIs, even for the most complex application. So that's the modeling part of things. A couple nice features here when you're all done. One of the things that I like to do is take pictures, right? And kind of what we have is a nice little export to PNG operation here. It basically lets you take this table structure and say, hey, this looks good. Let me put it on my design wiki. We can go ahead and save that and then go take a look at it and see what those PNGs look like. They're basically just screenshots of the table in aggregate. It outputs the table, each individual GSI. And again, when you design a model like this using kind of generic names for things, these are like entity names, it really gives you a good idea of what your data model looks like. It's kind of the best tool that I found to kind of represent what is actually there. Okay, we can export the data model. You can send this around to your team, put it into GitHub, do whatever you want with it. And then the next part of the tool, which is a really cool part of the tool, is actually the operation builder. Okay, so here's where we're actually going to take this model and we're going to stick it in to someplace. And so in this particular case, let's say well, actually, what's interesting is I can actually run operations against my existing. No, this is actually what I want to do is commit to DynamoDB. That's what I need to do. Commit the data first. And what I'm doing now is pushing sample data out to a real table. And I can actually design operations and queries against that real table and generate the code that you need to embed in your application. So it takes care of a lot of work for you. And so that's what this guy's doing now. It's just using my default connection configuration from my AWS CLI. It's going out there into US East 1, I believe. It's going to go create some table. It's going to insert all of this data on that table. And it should be done in a second here and let me know what it did. Yes, we can go ahead and open the table. Success. And
now you're here on the operation builder. And I have to say, this is another cool feature that you're about to show. The previous one about exporting to PNG is awesome. Like I had this small Choctaw at reInvent this last year, and I think I probably spent hours making screenshots of Excel spreadsheets, and then you change one character in the spreadsheet, then you have to copy it to screenshot, then put it back in the PowerPoint, find replace image. Yeah. It's a really amazing feature.
Yeah, no, it's cool.
I, Sean, have a question for you, Rick, about the model, because what you walked us through is really cool. Some people would like to get a copy of the JSON data model.
Absolutely.
And I have a copy that we were working on before that we posted in our Chime channel. Yeah. And if it's okay with you, I checked it. It seems to work. The data is clean. I'd like to go ahead and share that once we're done here, so everyone can do that data model and open it in their own NoSQL Workbench copy.
Yeah, I feel free. I think that's okay. Go ahead and post it. I'm sure it's the most current version. If you looked at it and it maps cleanly to what I just built, then yeah, absolutely.
Yeah.
Cool. Okay, so now we're out in US East 1. We're looking at the table that we just created. I can click on that table. You can see we actually have real live items. We can go ahead and build operations, actually validate our query conditions. And so, obviously our first use case is query by customer ID. So let's go ahead and, again, these are just sample items. They're using the exact same data that I plugged into the modeler. So absolutely, here we go, select by customer ID, you get the customer ID. I can pretty much guarantee you're going to get the same as you go across. We get all of our GSIs. We can look at the individual GSIs. We can query those GSIs. I can build operations against those GSIs. Let's query and say for GSI 1, this was order ID. And there was a date range to get and I think actually in this particular case, we want to just get the whole order history so we can execute that query. Oop, is that what we got? I must have typed something wrong. Oh, there's GSI 1. Yes. So, Yeah. Oh, it's not PK. It's PK1. What do you know? Because PK doesn't exist on GSI1. So we have PK1 is actually no partition key. Wait a second. I'm sorry. Select GSI1. Build operation for GSI1. Query partition key equals order ID. Execute. There we go. Yes, it's not giving us that nice aggregated view. That's what's confusing me. I love looking at the aggregated view. This is actually showing me the item view. These are all the items that came back. They all have PK1 of order ID, right? So that it's actually executing the query correctly. It's just my mind after looking at aggregate view. It's so pretty. I hate looking at these wide column things now. So that's actually something we could improve in the tool, is bring it back in the aggregate view. But anyways, you get the idea here. What we've got is a nice framework to be able to generate queries, validate your design, right? So this is what we're going to end up doing is you build this table. We have that table of 14 access patterns. What table, what index am I going to query? What is the key conditions that I'm going to provide to be able to retrieve the items I'm interested in? Now let's test it. Let's go ahead and commit this to DynamoDB, look at the sample table, run the queries, and validate that all of my design assumptions are working and I'm getting the item lists back that I would expect to see, right? So this is a really good tool to do that. The other things that we can do, which is just fantastic, is not only validate the query, but I can generate the code. And so let's just say in this particular case, we wanted to go, I think we were getting invoices by shipment. So we can say, give me everything for the shipment ID. And I can say, let's generate code. What does that look like? This is just Python code. You can cut and paste this. Heck, you can generate an executable binary, from this and download it if you want. It's really neat tool for both for all three, Python, Node.js, and Java, right? And so that you can, if you're not familiar with the DynamoDB SDKs, you can actually generate that sample code right here in the tool and just cut and paste it into your projects and just create a nice well-defined data layer API within your application space. So that's basically, I don't know, is there anything else that you think we want to showcase, Sean, at this point? I think I've pretty much run through the things that I wanted to run through. If not, we can maybe open things up for questions. We kind of wrapped up a few minutes early, but that just means we have more time for questions unless you got
a couple things come to mind. One, go ahead and grab those links that we dropped in. If you want to know what the access patterns were that we built into design, that's the first short link. The second short link, or actually the third one, because the second one had a little character on the end. The third short link lets you download the JSON module, JSON package that represents this model. Download that so you can reference it. You can load it into NoSQL Workbench. Now, if you would like to learn and really test your chops with NoSQL design in the future, after we're done today, there's a labs website, which we'll link to at the end, but I just want to tease it because I built it with the help of some of the other Dynamo SAs. I really like it. It's called AmazonDynamoDBLabs.com. AmazonDynamoDBLabs.com, you have scenario design challenges. You can try to design a schema in NoSQL Workbench for a bank and for a shopping cart solution so you can test your own chops. Well, that's a bit of a tease. There's a link to it that you'll see on the last slide. And of course, the slides will be made available in a PDF form. We have had a couple of questions over time. One question is about efficiency, because it seems that a design should be as efficient as possible. But what kind of consideration do you take whenever you are duplicating attributes? Because a lot of times, say you're making a composite key, you'll put like an order status in that key, and then it'll also be its own attribute. So obviously, Rick, that's going to be a larger item size. Is there any other considerations you need to take?
Sure. Yeah, I mean, again, what I like to emphasize, all the kind of modeling we did today was with kind of human readable attribute names, human readable attribute values. the machine's doing the reading. So, use meaningful abbreviations if you need to, but, generally, like I said, rely on the fact that the machine's doing the reading. So you can be able to use shorts, like, for status, a critical, just, use a numeric or maybe just C or, something like that. So it's not going to be that much larger to include these things in your composite keys. Composite keys grow when you start to use long, meaningful descriptive conditions and things like this. Try to avoid that stuff. As far as efficiency goes, what we're really concerned with is efficiency of processing. CPU is the most expensive thing, right? Storage is pennies per gigabyte. So it's do what you can to optimize the storage, but that's not terribly what we're worried about, right? What I'm more worried about is, hey, look, if I have to go run multiple queries to go traverse these hierarchical relationships, that's going to get expensive. And if I can project some of the immutable data that I'm really after when I make those queries, like, hey, maybe I want to know what was the PO for the items the customers ordered in our example, right? Do I need to really traverse the relationship to get the order object, or can I just decorate the items with the PO from the order? It's not changing. So this is the kind of things you need to think
I have
about.
a question for you. Linda asked, when you commit your data model to DynamoDB, can you make further changes to it in the data model and visualizer and then commit those changes?
When you commit the data to Dynamo, yes, well, you can, and you can't, right? I don't think that the tool right now will wipe existing items, but if you're updating or you're overriding the items, sure. But if you change the partition keys and the sort keys of the items that you're writing, and it's not going to remember that you had an old one with a different value, right? So you could end up with dirty data. Really, that commit to DynamoDB is purely, for me, it's all about validation of those access patterns, and I delete those tables almost immediately. As you can see, the items that live on the table are almost useless, right? They're just really there to describe the schema and to give me a kind of an actual working API with its that's absolutely, it is the real API for DynamoDB, so that I can validate my assumptions that when I make queries with these conditions, I'm going to get those items, right? So, it's kind of more or less they're temporary.
Yeah, and the operation builder is great. Speaking as a database solutions architect, once you create your design, you can make the image that has the data, what it looks like from the visualizer tab, put that on a wiki, and then in Operation Builder, construct your queries and get the code snippets and put that in the wiki too. And that's very powerful. Yeah. I do have a tip on NoSQL Workbench if you like to just expunge the data quickly. If you use DynamoDB local, with the in-memory option, it's a parameter that you pass in when it is launched. And if you're using DynamoDB local in the official Docker container, it is enabled by default. Once the container is stopped and started, or the jar is restarted, the data is gone. So you can quickly truncate the table by simply restarting Dynamo local, which is intended to just be a kind of transient, like quick unit test. Let's see if Dynamo is ready to go kind of database. I always think if I'm on a plane, then I use DynamoDB local. And if I have internet access, I would actually go for the real DynamoDB whenever I can.
That's same here. I mean, I bet that, like you said, pointed out, especially when you're doing like rapid fire debugging and you're trying to drop table. It's nice to be able to just have something like DynamoDB local where you can just, scrub the sandbox in seconds. Whereas, in DynamoDB, I got to create tables, tear them down, or use different table names. And if I'm running like, there's really no choice when you're running a high capacity. You got to go to DynamoDB. But, aside from that, I totally agree. One thing I wanted to show people at the end, this is kind of the final construct. When we talk about design wikis and we talk about, what do you do with the data model, this is the final construct that you're going to end up with. It's going to be a list of access patterns. We're going to have the entity relationship model. It describes all those things and how they're related. We're going to have a list of patterns to describe how they're actually accessed. And then we're going to have, these additional columns. Here's our 14 patterns. We've got, hit this table, hit this GSI, use these key conditions, use these filter conditions. Again, this was a relatively simple model. I've done some very, very complex stuff. Some of the moderators, I noticed Alex Debris is on the call. He's the author of the DynamoDB book. He took a lot of the patterns I talk about to another level in his publication. I definitely recommend that as a guide. And let's, honestly, when you start thinking about NoSQL, don't think about non-relational. It's not about non-relational data. It's all about relational data. So that's kind of it. So I think with that, what we'll do is we're going to go ahead and one last thing, obviously, I want to mention is, of course, lots of places to learn with AWS training certification, lots of resources out there for you. One of the things that Sean mentioned was DynamoDB Labs. Please go take a look at these. It's a really good tool to walk you through some of the basic access patterns and design patterns for DynamoDB. And at the end, it has some schema design exercises you can walk yourself through. You can actually use NoSQL Workbench to do that. And then you can kind of compare your design and what you came up with what some of the experts thought might be the best use cases for that. So you want to follow me on Twitter? I'm at Houlihan_Rick. I got Sean's.
It's like at Sean_Shriver. I got my name, but I just follow you in DynamoDB.
There you go.
Yeah.
That's right. Well, there's plenty of people to follow. You want to follow Alex Dupree, you want to follow me, you want to follow Jeremy Daly. He's got some really good content out there. There's all kinds of great people in the DynamoDB community. It's exciting to see how things have evolved and how things are growing over the years. This thing's really becoming a steamroller, and you're all part of it. So, again, any questions you have, let's go ahead and open the floor to you.
All right, first question is, it says, I was interested in seeing how facets are meant to be used. Is that something you can talk about? Rick, what do you think about facets?
Sure. So facets are interesting. I was, it was kind of something that when we were talking about the tool, we thought, hey, it'd be nice to be able to have logical groupings of these object types, right? And so when I show you the aggregate view, and the aggregate view has a partition, inside these partitions live multiple types of objects. Well, we were kind of thinking that, those objects are kind of facets, right? Each one of those type definitions defines a particular type of object. And since customers kind of like to use the tool that way, right? They wanted to, or were used to using relational tools, this way, defining a table to contain an asset, an entity type. We kind of thought facets might be that, but in reality, as we've started to use the tool, I think what you've seen is more along the lines of what I did earlier. We kind of create top-level attributes, keys, and GSIs, and use the aggregate view to what we're really more interested in as far as groupings. It's not groupings of object types, right? It's groupings of the objects within the relational structure that they're part of, and that's where partitions and hierarchies of items within the partitions comes in. So really, the aggregate view has become much more valuable. I'm not sure what the future of facets holds. There are users out there that are kind of creating this kind of grouping structure, but that's what they were intended to be. They're kind of more of a logical grouping of types as opposed to a real feature of the system.
Yeah.
I hope
question, do you know if .NET code generation is coming to NoSQL Workbench? I mean, generally, roadmap is something that's subject to change. We base it on what customers are asking for. So maybe this is really just a request to get the .NET added as a drop-down in the operation builder for NoSQL Workbench.
Yeah. I mean, I don't know if it's. I don't know. I kind of steer clear of roadmap in most cases, so I couldn't tell you specifically. I can tell you that, as with all other tooling, I would expect to see support for additional languages and additional platforms. So is it coming? Yeah, more than likely. When is it coming? I have no idea.
There's a clarification question. It's actually really not about your design, but Dynamo in general. Can you apply, from John, can you apply a filter on fields inside a data blob? And when he says data blob, I think that's a map.
Yes. Yeah, if you're referring to a map, absolutely. You can reach down inside of that map and you can apply filter conditions to any of the attributes within the map. This is one of the reasons why I say when I'm creating DynamoDB objects, I will only project to the top, to the root of the item. I'll project my indexed attributes. That's when you look at the NoSQL Workbench. If I have any attributes that I'm including in the filter conditions that live inside the map, I might have a little map object in the Workbench that demonstrates, hey, here's some filtered attributes, but I don't necessarily put all the extended attributes in there. But yeah, the top, long story short, yes, you can use map attributes as filter conditions.
Let's see, find another question here. The question was if the data model would be available. Yes, it is in the Q&A. Let's see if there's any new questions that have come in. It's good. I think we've answered so many, thanks to Rob, Alex, and Pete for replying to you guys directly so you can get those answers. Oh, we're going to go and pop the poll up.
All right, so we're putting up some content right now for you guys to take a look at. How'd you like the webinar today? Hopefully it was not too many hiccups. I think we got through it pretty well. We'd love to do more of this stuff. Your feedback's very valuable to us, so please take a second or two and just fill out all the questions there. And thank you so much for taking your time out of your day to come and learn a little bit more about DynamoDB. It's definitely a subject that is near and dear to our hearts. So
yeah, thank you very much for coming, guys, and for everyone for asking these questions. I appreciate the questions that you've asked, and if you have any more, we'll answer them while we're still here. There's a field here where you would ask, you could say if you would like to do a follow-up, and if our ask of you is in the question, if you say that you would like a follow-up, then please put your email address into the last question. We will look for people who have asked for a follow-up, and then we will check the email address and use that to link back to you so we know who has asked for us to contact you.